Hello everyone. In this session, we will discuss about probability density function, its definition, properties, and then deal with the examples. So first let's start with the definition of the PDF, probability density function. PDF of a random variable capital X is defined as fx of x is equal to d by dx of fx of x. So if you see the small fx of x, this represents the probability density function. Probability density function of the random variable x corresponding to the independent variable small x. And your capital Fx of x represents the cumulative distribution function. In short, CDF, cumulative distribution function. So we can also say that the change in the cumulative distribution function is named as probability density function. So to understand the PDF, let's consider an example. So let's consider an example of rolling a dice. Consider an example of rolling a dice. So assume the dice has 6 faces. So let's x be the random variable which takes the face values observed when we roll the dice. So first x is equal to xi. So your random variable x takes the values 1, 2, 3, 4, 5, 6. And the probability of observing 1 when we roll the dice is 1 by 6, because total number of outcomes are 6, and in each and every case there is only one favorable outcome. So they are all 1 by 6. Nothing but it is an example for the equally likely events, because the probability of all the events is same. And it also stands an example for the mutually exclusive events. So mutually exclusive is like when I roll the dice, if I see a 1, so there is no chance that I will find a 2, 3, 4 or 5, 6. So this makes it as a mutually exclusive event. Now if we try to plot the cumulative distribution function of this random variable. So you know that the CDF, cumulative distribution function, represented with fx of x. So fx of x, by definition, it is nothing but the probability of the random variable x taking the values less than or equal to x, by definition. So fx of 1 will be 1 by 6. Fx of 2 is equal to 2 by 6. Fx of 3, 3 by 6, 4, 4 by 6, 5, 5 by 6 and 6, 6 by 6, which is equal to 1. Now let's plot the CDF of it. So your random variable x is a discrete random variable. So what we see is also a staircase waveform. So always a CDF starts from 0 and it will end at 1. Now as per the values at fx of x, fx of 1, at fx of 1 it is 1 by 6. So this is 1 by 6. And at fx of 2, 2 by 6, 3, 3 by 6, 4, 4 by 6, 5, 5 by 6, 6, 6 by 6. And the jump at each random variable, the jump at each value of the random variable will be equal to the probability mass function at that point, PMF, probability mass function. So for more details on the cumulative distribution function and how do we plot the graphs, you can refer to my earlier videos. So once after we plot the CDF, so now observe the CDF. So if you see from x1 like xi, like if you take from minus infinity, if this is your minus infinity, from minus infinity to 0, from minus infinity to 0, that is when xi is equal to minus infinity to 0, there is no change in the cumulative distribution function. So when there is no change, the change in the CDF we consider it as a PDF. So when there is no change in the CDF, TDF will be equal to the probability density function at this point will be equal to 0. And that xi is equal to 1. See here, when xi is equal to 1, at xi is equal to 1, CDF changed by 1 by 6. From 0, it changed to 1 by 6. So the PDF at xi is equal to 1 is 1 by 6. Now at xi is equal to 1 to xi equal to 2. Now from here to here, again there is no change in the CDF. So once there is no change in the CDF, the PDF also will be equal to 0. Now again at xi is equal to 2. At this point, CDF is changed from 1 by 6 to, there is a jump from 1 by 6 to 2 by 6. That is 1 by 6 is the jump seen. Therefore, the PDF will be equal to 1 by 6. So the same thing you can observe at each and every point. At 3, again there is a jump from 2 by 6 to 3 by 6, which is equal to 1 by 6. At 4, 3 by 6 to 4 by 6. Again the jump seen is 1 by 6. Nothing but equal to PMF, probability mass function. Now from these observations we can plot the PDF. So at x-axis we take the random variable x, and on the y-axis small f x of x, which is nothing but your PDF. And at the values 1, 2, 3, 4, 5, 6, it is equal to 1 by 6. Therefore, from this we can understand that the probability density function of a discrete random variable is an impulse train. Impulse train of what? Of a discrete random variable. The PDF of discrete random variable is equal to is a impulse train. Now the PDF of a random variable can be expressed as, by definition we know that fx of x is equal to d by dx of f of x, derivative of a CDF cumulative distribution function fx of x. So d by dx of this can be written as, now if you observe the cumulative distribution plot, the fx of x can be written as a function of unit step function. So d by dx of sigma for the values I, p of xi into unit step function u of x minus xi. And we know that the derivative of unit step function is a delta function. Unit step function, the derivative of it is delta function. So substituting this, we get it as sigma p of xi into delta of x minus xi for the values of x is equal to I. So here we are representing the delta of x minus xi is nothing but saying it is an sequence of impulses or train of impulses with the coefficient probability as the coefficient p of xi. So now let's see the properties of probability density function. So the first probability, fx of x greater than or equal to 0. So how do you understand this? Since PDF is the change in CDF, already we have seen this in the definition, and CDF always changes by a non-negative amount, that is nothing but by the probability of the random variable. So PDF is, so from this we can infer that PDF is always a non-negative number, therefore fx of x is greater than or equal to 0. Now the second property, integral minus infinity to infinity fx of x into dx is equal to 1. So we know that by definition, fx of x, which is your PDF, is equal to derivative of CDF. Now integrating on both sides, fx of x into dx is equal to integral minus infinity to infinity d by dx of fx of x into dx. So this is equal to integration differentiation get cancelled, fx of x between the limits minus infinity to infinity. And now this we can write it as fx of plus infinity minus fx of minus infinity. So we already know that from the properties of the CDF, that fx of plus infinity is nothing but equal to, this term is equal to 1 from the properties, and fx of minus infinity is equal to 0. Now substituting this, we can write it as integral minus infinity to infinity fx of x dx is equal to 1 minus 0 is 1. So this statement it also states that total area under PDF curve is unity. It also states that, so you may be also asked like, prove that the total area under the PDF curve is unity. So the same proof, whatever we have seen for this second property, you can write down this. It states that the total area under PDF curve is unity. Now let's go for the third one. So fx of x is equal to integral minus infinity to x fx of x into dx. So again we'll try to go with the proof of this property. Now by definition again you can write down that fx of x CDF is equal to derivative of, PDF is equal to derivative of CDF. Now again integrating on both sides, integral minus infinity to infinity fx of x dx is equal to integral minus infinity to infinity d by dx fx of x into dx. Now this can be written as fx of x between the limits minus infinity to x this is equal to fx of x minus fx of minus infinity, and you know that fx of minus infinity is 0. So we can write that fx of x is equal to integral minus infinity to infinity fx of x into dx. So here if you see fx of x minus fx of minus infinity, so this is minus fx of x minus 0 is equal to fx of x. So we can write that fx of x is equal to integral minus infinity to infinity fx of x into dx. So this is the proof for the third property. Next, fourth one, probability of random variable x greater than x1 less than or equal to x2 is equal to integral x1 to x2 fx of x into dx. Now considering the right hand side, integral x1 to x2 fx of x into dx is equal to fx of x between the limits x1 to x2. So this can be written as fx of x2 minus fx of x1. So you know that the cumulative distribution function, by the definition, fx of x is equal to probability of random variable x taking the values less than or equal to x. So this can be written as p of x1 less than x less than capital X less than or equal to x2. So these are the four properties and their proofs. So now let's see some examples. So example 1, suppose we have a random variable x and we know that it has a triangular probability density function as shown in the picture. So fx of x is equal to the probability density function fx of x is equal to 0 for x greater than 3, x between 3 and 13, and x minus 3 by 25, and x between again 3 and 8, and 0.2 minus x minus 8 by 25 for the value x greater than or equal to 8 less than 13. So now the question is, find the probability that x has values greater than 4.5 but not greater than 6.7. So what they are asking is, given the PDF, they are asking us to find out the probability of the random variable x greater than 4.5 but not greater than 6.7. So probability of x greater than 4.5 less than or equal to, but because they have given test not greater than 6.7. Now from the property. So from the property, fourth property, see here, P of x1 less than random variable x less than or equal to x2 is equal to integral x1 to x2 fx of x into dx. So substituting the values in this property, integral 4.5 to 6.7, because 4.5 to 6.7 this is valid. So we take x minus 3 by 25 dx. So solving this simple integration, 1 by 25 into, taking the constant out, x square by 2 minus 3x, limits 4.5, 6.7. So this is equal to 0.2288. Now we can write it as probability of x having the values greater than 4.5 but not greater than 6.7 is equal to 0.2288, or in percentage 22.88%. So this is how we find the probability from the given density function. Second example, a random variable x is known to have a distribution function fx of x. Cumulative distribution function is given, which is equal to u of x unit step function into 1 minus e power minus x square by b, where b is greater than 0, is a constant. Find its density function. So given CDF, we need to find out PDF. So fx of x is equal to u of x 1 minus e power minus x square by b. This can be written as u of x d by dx of 1 minus e power minus x square by b plus 1 minus e power minus x square by b into d by dx of u of x. It is like applying d by dx of uv formula, product rule, which is equal to u into dv by dx plus v into du by dx. So this can be simplified as u of x d by dx of year 1 is 0 minus e power minus x square by b, because e power x is equal to the differentiation of e power x is same e power x. So e power minus x square by b into minus 2x by b. Nothing but differentiation of minus x square by b is 2x by b, plus, so taking the term 1 minus e power minus x square by b as it is, d by dx of u of x, derivative of unit step function is delta function. So delta of x. So simplifying it, u of x, so 0 minus into minus plus e power minus x square by b into 2x by b plus delta of x into 1 minus e power minus x square by b, which is equal to u of x into e power minus x square by b 2x by b plus delta of x into 1 minus e power minus x square by b. Now the second term will become 0 because it is an impulse function. Impulse function becomes 0 at the when x is equal to 0. So therefore you can write it as now fx of x PDF is equal to u of x into e power minus x square by b into 2x by b. So this is your final answer. So this is an example stating how to find out the probability density function given the CDF, cumulative distribution function. So all we need to do is a differentiation. So hope this video will help you to understand cumulative distribution function, its properties, and also how to apply in solving the problems. Thank you all.